So another surface of revolution is just take a straight line parallel to the z-axis, rotate. So what are you going to get? A circular cylinder, right? Like that. So one in the list we didn't look at that time. So this is just x square plus y square equal to 1. In R3 it represents a cylinder. There is no restriction on the z coordinate, right? So only the x and y coordinates have to satisfy this. So they always lie on a circle. Circles parallel to the xy plane, right? So stack one circle on top of the other. So you're going to get the cylinder. We'll come back to this later. So this is what is called a helicoid. Heard of helix? A curve called helix. So you have the cylinder, just spiral which winds around the cylinder, right? So this is the three-dimensional version of that, surface version of that. This is a helicoid. You might have seen what are usually referred to as spiral staircases, right? So those are precisely these helicoids. Take something like this. What does this give you? So always points lie on some circle or the other. Take Z. If you fix a Z, you have the unit circle at the point lies on the unit circle at that level. You don't get the whole circle, so but it keeps winding like that. Of course, helix is famous from other contexts, biological context. What is called DNA is the structure of DNA is what is called a double helix. So the famous Watson and Crick, they got the Nobel Prize for that. But actually, the person who first found out this structure was uh, Rosalind Franklin, I think. Rosalind Franklin. I'm not sure about this, but this certainly is. So, as happens many times in these awards, whatever level, awards at whatever level, it was Nobel Prize or Field Medal, anything, always there is something involved. So the point was, of course, that Watson and Crick did not even refer to Rosalind's work. So all the basic work was done by her. Okay, so we'll be coming back to more examples as we go along, various contexts. Maybe I'll give you one example of one surface in n plus 1 space. It is not usually discussed in any of your books. Rather, not n and n plus 1, but n square and n square minus 1. Let us look at the lower dimensional case. Look at all 2 by 2 matrices. Real. So what is the dimension here? This is R4, right? So 4-dimensional. Look at X here. Determinant is equal to 1. So, okay, let us write a 2 by 2. So, x11. So, this is a matrix. So, what is the determinant? 2 by 2 matrix. So, x11, x22 minus x12, x21 equal to 1. So, you can think of this as all points in R4 satisfy this condition. So, this is a 3-plane R4. This is a level surface, right? F of x11, x12, x21. So instead of writing x2, x1, x2, x3, x4, we write like that, okay? Because you have matrices, is this one. So all points where f is 1, so this is f inverse 1. So this is a level surface, but we have to check the regularity condition again. So you have 4 partial derivatives, right, with respect to each of these variables. So what is, so let's write 1, 1, 1, 2, so on. So del 1, 1 f is x22, right? Del 1, 2 f is minus x21. If all of them are 0, then what will happen? You get the 0 matrix, 0 in R4. But that cannot satisfy this condition, right? So every point, therefore, is a regular point on SL2. So every point so what is the conclusion? This is what we have called SR 3 surface in R4. Because there is nothing special about 2 here, you can take any matrices of any order. So M and R the dimension is n square for the space M and R. There is only one condition, only one degree of constraint there. So this is going to be n square minus 1 manifold, submanifold of this. So again, the same kind of argument, derivatives. But tell me now, how do you say, here we had 2 by 2, so we explicitly wrote down the determinant x11, x22 minus blah blah blah. But you then differentiated. Okay, so how do you differentiate a determinant? So if you have a a determinant like this is a function of m square variables, right? So if you want to find, for example, how do you do it? Can you write down what this is? What this partial derivative is? You know how to expand the determinant, right? Rows by rows or by columns or whatever. So how do you expand? 1 times the n minus 1 by n minus 1 determinant. X minus, x11 will it occur in either place? Every time. So if you expand by second column, there will be an x11. So writing down these things is, but how do you differentiate without expanding? Have you seen it anywhere? Or you have any idea about how to go about it? Okay, you think about it. Okay, you'll come back to this. You spend some time on trying to see how to do it. Okay, so expanding, you won't end up anywhere, right? It's complicated calculations. But without actually expanding the determinant, how can you differentiate this function, determinant function? We'll do it in a slightly different context shortly, but so try to think about this, how to go about it, okay? Now, in any case, so the conclusion here is the same as before. SLNR is an n square minus 1 surface in Rn square, okay, or M and R. So we also defined tangent vectors yesterday, right? So let's recall the definition and try to calculate some tangent vectors. As in n surface, always this will be the P the point in S, V. So let me use the notation that was used yesterday. So this is PV, right? According to yesterday's what Dr. used. This is a tangent vector to S at P if there is a parametrized curve alpha. Alpha is easier for me to write rather than gamma. Gamma, if I write it is gamma or R or what. So I will write alpha. Such that alpha on S, that means alpha t lies in S for every t, such that alpha 0 is P and alpha prime 0 is vector V. So we are using this arrows for tangent vectors and vector fields, right? So he is using that, so let me also use that. Normally I don't write. So just to distinguish between the point V and vector V. So elements of the tangent space are vectors, right? So now the point here is you have essentially proved this, but we will write down the proof time. So all tangent vectors at tangent vector to S at the point P, right? So we will write TPS instead of all tangent vectors to S at P. The result is that this is nothing but gradient F at P, the orthogonal complement of the gradient. The gradient is what? What is F? From the definition of S. So S is equal to the level surface of the smooth function F. So F is not mentioned, it's always like that. Okay. So level surface given by the function. So the gradient of F. So this is just the partial derivatives, right? Del 1 F at P, del n F at P, the vector. So at least one of the partial derivatives is not zero by definition of regularity. So this is the one-dimensional space, right? Del Fp is P variables. So this is the orthogonal complement of non-dimensional subspace in Rn plus 1. So it is an n-dimensional subspace of Rn plus 1, right? So the orthogonal complement in Rn plus. See, from the definition of a tangent vector, just by looking at the definition, it is not even clear whether it is a vector space, right? If you add two tangent vectors, are you going to get to? That's not obvious from the definition. But once you have this, you not only see that it is a vector subspace, but you even know what its dimension is. So this is of course called the tangent space at P to the surface S. Geometrically, so this is a subspace, okay? So if you, in Rn plus 1, so it passes through the origin, right? If you look at a sphere, any matter, so if you look at the tangent plane at a point P, it passes through P, not origin, right? So geometric tangent plane is different from this tangent plane. So, but what is the relation? Geometric tangent plane will pass through the origin. So it's just a translate of that. So translate this actual geometric tangent plane to the origin to get this TP. So this is a translate of. So the geometric tangent space at P to S is translate of this by P. See, remember TPRn plus 1. What was TPRn plus 1? So all pairs P comma vectors in Rn. So it is a P cross Rn plus 1. So it doesn't pass to the origin, right? So it is Rn plus 1 with origin shifted to P, essentially, right? So it's exactly the thing which happens to the subspace here. So this is a subspace of this, if you look at that way. So if you look at TP Rn plus 1 as Rn plus 1, then TP is a subspace Rn. I mean this. So always the translate is involved because subspaces have to contain the origin. So from the point on the surface, you come back to the origin. So let's compute some examples of tangent spaces. So example, so that so you don't see in your books. So we'll prove this subsequently. But it's quite simple. In fact, if you remember the integral theorem on integral curves, existence, uniqueness, maximal integral curve, proved yesterday. The last part of that, if you look at the proof, it's more or less one part is just chain rule. The other part is almost the same as the proof of part 3 of that theorem. We will write it down sometime later. Okay, let us again first look at 2 by 2 case before we pass on to general case. Let us try to compute space to this at the identity matrix. To make things simpler, let us take the identity matrix. So what is Ti? So for this, what do you have to do? What is a tangent vector at the identity? So you have to first take curves through identity and take the tangent vectors. So first let us try to look at some curves in SL2. Right? Curves in SL2 are 2 by 2 matrices depending on the parameter alpha 1 1 t, alpha 1 2 t, and so on. Right? The curve in SR is of the form the components are this, okay? And with the condition, because the determinant condition is there, to alpha to 1 equal to 1 at every point for all t, right? So give me some examples of such things. Let us first look at some examples of such curves here, okay? So, for example, right? E power t is 0, 0 e power minus t. The determinant is what is alpha 0? So this is your alpha t. Alpha 0 is identity matrix. What is alpha prime 0? You have to differentiate these things. E power t 0, 0 minus e power minus t. Right? Evaluate at 0, 1, 0, 0, minus 1. Right? So this is one tangent vector to R. Give me another curve. Rotation, right? T sin t minus sin t cos t. Okay, for this also alpha 0 is identity. Then alpha prime 0, alpha 0 is I, alpha prime 0 is what? 0 0 1 minus 1. Is that right? Is there any property common to this and that? Here 1 and minus 1 are the eigenvalues, right? What is the sum? 0. So what is 0 in this case? What is the sum of eigenvalues? Is the trace, right? This also has trace 0. So you make a wild guess that all tangent vectors are going to have 0 trace. But is that true? Or can you say the other way? If you have a matrix whose trace is 0, then it is a tangent vector. There are two things, right? One statement that every tangent vector has trace 0. The converse, every trace 0 matrix gives you a tangent vector. Both look to be true. Which one looks easier? See, starting with any matrix, how to get an invertible matrix, for example. Look at the exponential. Remember the exponential that we discussed as an application of the inverse function theorem. Okay. So e power x is given by the usual series for any matrix, any n by n. If you want. There's no problem about convergence. It's absolutely convergent, whatever. And so if you want a curve, just put a t there. Right? Alpha t defined as fix an x, take alpha t to be e power tx. Okay? In general, of course, this is a non-singular matrix. E power x is always invertible. E power x into e power minus x is identity. So e power tx is invertible. So alpha 0, it passes through the identity matrix. E power 0 is identity matrix. What is alpha prime 0? X e power tx. So this is going to be x. Alpha prime t is x times e power tx. I'm leaving some of these for you to verify. We had done this earlier in one of the classes when we discussed inverse function theorem. So alpha prime 0 is x. So you get that this shows, for example, that x is an arbitrary matrix. So every n by n matrix is a tangent vector at the identity to, for example, all non-singular matrices. Right? This is always non-singular. So this is a curve in GLNR. But now we are not interested in GLNR as it is, because GLNR is not surface in our sense, right? It is an n square dimensional manifold in n square dimensional space. So you want this to be in SL2R. So when does this belong to SL2R? Or SLNR? Meaning, when is determinant of e power x equal to 1? For what x? Right? But what is determinant of e power x in general? If x is a diagonal matrix, for example, what is e power x? What will be the powers? What is x square? Lambda 1 square, lambda n square. So x power k will be lambda 1 to the k, lambda n power k. So everywhere you will get powers of the diagonals only. So you get diagonal matrix again. So the diagonal elements will be e to the lambda 1, e to the lambda 2. What is the determinant in this case? E power lambda 1 lambda n. This is nothing but e power trace of x. This is for a diagonal matrix. What about a triangular matrix? It's not diagonal but triangular, so doesn't matter. Something is there instead of 0, but still the determinant is going to be the same, right? Even for a triangular matrix. Right? What I have to write determinant here, right? So for a triangular matrix, the determinant of e power x is e power trace of x, right? What about a general matrix? Any matrix can be triangularized. Not all matrices can be diagonalized, but all matrices can be triangularized, which means what? There is some whatever A, so that AX A inverse is triangular. What is the exponential now? You have to add the powers of this, right? This is sigma AX A inverse power k by k factorial. But what is this? AX A inverse AX A inverse, so on. So all these A's which lie in between will cancel off, leaving you A inverse on this side, A on the other side. In the middle you will have only the x's. So we will x k times. So this is A inverse, A this side, okay. A x to the k, A inverse. So this is right. For any matrix, if you which is similar to a given matrix, if two matrices are similar, they have the same everything, right? Eigenvalues, determinant, trace, everything. So determinant of x is going to be, so determinant of A inverse, exponential of this is going to be, this is a triangular matrix. So by what we have said here, it's going to be the trace of A inverse, right? So the trace of A inverse is same as trace of A, right? So, so all these quantities are invariant under similarity transformation. So determinant is also going to be the same. Determinant of this is also going to be determinant of A power x. So what is the conclusion? So this and this will have the same determinant. So that is the same as the trace of this. That is the same as trace of x. So the conclusion is that determinant of e power x is equal to trace of x for every x, right? E power trace of x. So if you come back to our example, we are in SLNR, so determinant is 1. So if the trace is 0, if trace of x is 0, then determinant of e power x is 1, right? So if trace x equal to 0, then determinant, then e power x is in SL. And therefore, of course, the curve e power tx is also in, for every t, the same thing is true. Trace of tx is t times trace of x. So in this case, alpha t equal to e power tx is a curve, parametrized curve in SLN. Through I. Alpha 0 is I. And so alpha prime 0 is x as before. So what have we proved? If you start with a matrix of trace 0, then it is a tangent vector, right? So x has trace 0, trace x equal to 0 implies x is in Ti. Or what is the same? If you look at all x in M and R, trace 0, so this is contained in the tangent space SLNR. Okay, yeah. So we have one enclosure. What about the other enclosure? Suppose you have a curve alpha ijt. This is in SLNR, right? What can you say about alpha prime 0? How do you calculate? So now again, this is in SLNR, which means that determinant alpha ijt is equal to 1. What does this give you? If you differentiate both sides, so alpha 1 1t, alpha 1 nt, alpha n 1t, alpha n nt, this determinant is 1. So differentiate with respect to t now. So this side you have 0. So let us bring it on this side. It's equal to, now back to the same kind of problem that we encountered earlier. How to differentiate the determinant? You know the definition of determinant as a sum. I mean, this is just the way you expand the determinant. But was it sigma minus 1 to the power sigma varying over all permutations? No, you don't know that? Anyway, so let me not get into that now. So how to differentiate this? I'll give you the rule. You see whether you can prove that. Okay. So once you, you can try to prove that only if you know the definition of determinant. Write down the expression for a determinant. Okay. So anyway, so what you have to do is, so you have entries here. So each of them is a function of t, right? You want to differentiate with respect to t. So differentiate one row at a time and add. That means, so first differentiate the first row. So what are you going to get? Alpha 1 1 prime t. Oh, dash, I keep writing dash for dot, okay? Alpha 1 n prime t. And I will keep the rest as they are, as alpha 2 1 t, whatever. So you have then nothing to the other rows, you have just differentiated the first row. Plus, you do the same thing for every row. Differentiate the second row, keep the other rows the same. The last term will be alpha 1 1, alpha 1 n, blah blah, alpha n minus 1 1, alpha n minus 1 n, alpha n1 prime, alpha nn prime. So this is going to be sum of n determinants got by differentiating one row at a time. So this, of course, now instead of looking at one determinant, we have to calculate n determinants. But to simplify things, we calculate it at alpha equal to 0. Right? We want only the tangent vector at the identity. So evaluate at 0. tangent, so alpha 0 is I. Okay, so you want to see what alpha prime 0 is. So alpha 0 is I. If you evaluate this at 0, what are you going to get? The first row is something, each evaluated at 0, but what about the other terms here? The diagonal terms are all going to be 1, all other terms are going to be 0. So you are going to get something like, this determinant is of the form alpha 1 1 prime 0 blah blah alpha 1 n prime 0 and then 1 1 1 like that and 0 everywhere else. So this determinant is now is a triangular matrix, so just the product of alpha 1 1 prime 1 1 1 1 1. So this first term is just going to give you only alpha 1 1 prime 0 and same way, so this is going to give you alpha nn prime 0. So this is a tangent vector, this is your x, right? So what do you get therefore? Alpha 1 1 prime 0 plus etc. alpha nn prime 0 is equal to 0. On the other side you have 0, okay? But what is this? Alpha prime 0 is x. So these are the diagonal elements of x. This is x11, xnn, right? So it is just the trace of x. So in other words, what? If a vector, if a matrix X is a tangent vector at 0, it has 0 trace. And conversely, if we have seen the earlier, the other way, if you have a matrix of trace 0, then it is a tangent vector, right? So X is in Ti SLN implies trace of X equal to 0. That's what we have arrived at here. Conclusion, therefore, combining this with the earlier one, we are going to have that the tangent space at the identity 2SLNR is the set of all matrices of 0 trace. So we have at least calculated one good example of a tangent space. So you can also observe something here. So what do you know about the trace function? Trace gives you a linear functional on the space of all matrices, right? And the null space or the kernel of a linear functional, what do you know about that? The null space of a linear functional, non-zero, okay, it's not a zero functional, then the null space is going to be a hyper subspace, one dimension less than the whole space. So this is going to be an n square minus 1 dimensional subspace of all of Rn square or Mn R. Okay? Of course, this we know from what we have said because we have realized this as a tangent space, so it is of dimension n square minus 1. But you observe that just from the fact that trace of x equal to 0, I mean, it gives you that it's a linear functional kernel of the linear functional trace functional, so has dimension m square minus 1.